So for this video, you're going to need your Halloween party candy problem that we started in class, and then also a sheet of paper. So I'm going to go ahead and get started here. We are on assignment 13, 3.6, solving systems of linear equations. And 3 variables. Okay, essential question. How do you use and solve systems of linear equations and 3 variables? And as you saw in class today, in order to even make this happen, you're going to need 3 different linear equations in order to be able to solve it when there's 3 variables. Just like when we had 2 equations with 2 variables, we were able to solve it because we had those 2 equations. So if you had 4 equations, you would need to have 4 variables in order to solve. And that would just get really complicated. I will be showing you another method of solving these, but in the meantime, it's important that we understand how to do the simple math behind all of this. So let's go back and, actually, let's start with this. So the first thing, if you have 3 equations with 3 variables, then your solution now is not an ordered pair. Your solution is an ordered triple. Okay, so your solution will have like x, y, and z. So this basically means that we're going into the 3rd dimension. You're no longer in a 2-dimensional coordinate plane where you have x and y just flat on a paper. You now have this 3rd dimension. Imagine it kind of popping out at you. Okay, which basically means that we're looking for where planes intersect. Okay, it could intersect at a point, it could intersect at a line, or there could be absolutely no intersection of the planes at all. That is explored more on page 177 if you wanted to read through that. I would recommend that you do, but that way you can understand what these solutions actually look like. I am not having us graph these because it's kind of a waste of time. It's really confusing. There's computer programs that can do it a lot better. And I will show you something in class that shows you how this is done. Okay, so I gave you a problem. In order to save some money this Halloween, I am thinking of having a Halloween party and telling my friends that they can come to my party as long as they bring candy. That way I don't have to spend $1 million on candy. Or $100 on candy. So all my friends decided to buy candy, and they all decided to buy the same kind of candy, and they spent different amounts. And so we explored this. We gave all of our unknown, being the cost per pound of each type of candy. We gave them variables, and then we wrote equations. Notice all of these are to the 1st power. All of our variables are to the 1st power, so these are linear equations. Okay, and so we want to now figure out a way to figure out what is the cost per pound of jelly beans, chocolates, and caramels. So this is a lot like when we did it with 2 equations and 2 variables. We're just going to add an extra step. Okay, and I'm going to use combinations the whole time. You can definitely use substitution, but I'm going to show you using combinations. Okay, so I'm going to work on this other sheet of paper, but I'm going to work with these 3 equations. So I'm going to go ahead and write these down. And maybe you have used different variables. It would be good if you could change those variables now to look like mine. That way it's not too confusing for you. Okay, so my 3 equations are 1j plus 5c plus 1r equals 16. And 3j plus 3c plus 2r equals 25. And 1.5j plus 2c plus 2r equals 16. Okay, so we need to solve this system. Okay, so the first step you're going to do, and I will write out steps because this gets pretty complicated. Not complicated, I'm sorry. It just gets really lengthy, and if you're not super organized and following the steps precisely, you could end up making some mistakes. Also, your arithmetic is going to be really key here because this is a very long problem. It takes basically twice as long to do this as it does to solve a system with just 2 equations and 2 variables. So you want to be really careful with your work. All right, so we are going to eliminate one of the variables in 2 of the original equations two times. So what we're going to end up with is 2 new equations. So we'll end up with 2 new equations in 2 variables. Okay, so I'm going to number these. This will be my first equation, my second equation, my third equation. Okay, so I'm going to start with my first 2 equations. So I'm going to write just 1 and 2. So 1j plus 5c plus 1r equals 16. And 3j plus 3c plus 2r equals 25. Okay, so my goal right now is to get rid of one of my variables. Probably the easiest one to get rid of with the smallest numbers here would be my r's. So I'm going to multiply this top one by a -2 so that way my r's will cancel out when I add them together. Okay, so this equation then becomes -2j, right? I'm just distributing. And if you still didn't understand our lesson with 2 equations and 2 variables, I would recommend going back and watching that video before you continue on. Okay, so this gives me -10c minus 2r equals -32. And then I'll just rewrite this one. Combine them or add them together. So I get a positive j, a -7c, and basically my r's are gone, and that all equals -7. Okay, so I did it with the first 2 equations, and now I'm going to do it with the next. I'm going to basically do equation 2 and equation 3. I'm going to eliminate the exact same variable, so I'm going to eliminate r again. Okay, so equation 2 and equation 3. Okay, so now I want the r's to cancel out. So that means, well, right now they're exactly the same numbers, so I need them to be opposite. So I'll multiply the bottom by a -1. So I get 3j plus 3c plus 2r equals 25 for that one. And then this one becomes -1.5j, -2c, -2r equals -16. When I add those together or combine them, because I'm using linear combinations here, I get 1.5j plus c, the r's are gone, and this would give me 9. Okay, so that's my first step. And here's the cool thing. Let me get a highlighter if I have one. You'll notice that these 2 equations look just like what we had before. So a couple lessons ago, we basically had 2 equations with 2 variables, right? We have now eliminated all the or the third variable. So now it's just like we used to do a couple lessons ago. I'm going to label these equation A and equation B. All right, so step 2. I'm going to solve the new system of equations in 2 variables. So that's basically just looking at equations A and B. Okay, so first equation, equation A, j minus 7c equals negative 7. And then equation B, 1.5j plus c equals 9. So what I might want to do is I might want to multiply this bottom one. Well, I could do this a couple of ways, but I think I'm going to multiply the bottom one by 7. So that way my c's will cancel out. Okay? So I'll multiply this one here by 7. So the first one stays the same. And then this one becomes, oh, what is that? 10.5 plus 7c equals 63. So now I'll combine those. I get 11, oops, that's a j. 11.5j. The c's go away, and I'm left with 56. Solving for j. J is going to give me 4.869565. Now, yeah, I'm talking about money, but right now I don't want any rounding. I don't want to round too soon. So I'm going to go quite a ways. Okay, here I'm using 6 decimal places. I'm going to go quite a ways because what could happen is that I could round too soon here, and then my numbers will be pretty far off. Okay, so by rounding too early in the game, you will have some issues. All right, so I know then that jelly beans are going to be about $4.87 a pound. Okay, so now what do I do? Well, now I can take, so this is one of my answers, but can't I now take this and plug it back into either one of these 2 equations? And then I'll be able to figure out what C is. Okay, so I'm going to have to flip over. I'm sorry. I'm going to use the first equation. J minus 7c equals negative 7. And again, I'll just plug in J, which was 4.869565 minus 7c equals negative 7. So now I'm going to need to subtract this. And I'll get negative 7c equals negative 11.869565. And now I'll divide by negative 7. You want to make sure, right, if I'm talking about cost per pound, I shouldn't end up with any negative answers. So I'm going to do and I'm getting cost of chocolate per pound is about 1.695652. Okay, so I've got that. So I've got 2 of my variables solved for. Cost of jelly beans per pound and the cost of chocolate per pound. And so now it should be really easy to figure out what the cost of caramels are going to be per pound. I can choose any of my original equations to plug it back in. So step 3, we're going to find the third variable. By substituting substituting the two variables found in step 2 back into one of the original equations. Okay, so I'll pick one of the original equations. How about the first one? So the original equation was 1j plus 5c plus 1r equals 16. Let's see, c was that. So let's see, j was, let me flip my page back over, sorry, 4.869565. C was 1.695652. And I don't know what R is. That's what I'm looking for. Okay, so this becomes just 4.869565 plus 8.478260 plus 1R equals 16. So I'll combine these two. End up with 13.347827 plus 1R equals 16. And then I will subtract this from both sides. And I'm showing a lot of work here. You can definitely do a lot of this on the calculator and maybe not have to show as much work, but I feel like it's important for you to be able to see my steps. So I want to give that much to you guys. So I've got 1R equals, and then I'm just going to subtract that. And I got 2.652174. Okay, so in conclusion, I know that, let's see, caramels are $2.65 per pound. Is that how you spell caramels? Oh, hopefully. I think so. Okay, and then chocolates are, and I will round up here. So I'm going to round it to $1.70, which means that when I go back and I plug these back in to check my answer, you know, it's going to be a little bit off. It's going to be, you know, maybe a cent or two off. Okay, not that big of a deal. Oh, so I said I was going to round up to 170. So $1.70 per pound. And the last thing that we had was jelly beans. Now, I don't know how accurate these prices are. I made this problem up, so, you know, I'm not sure if jelly beans would be that much more expensive than everything else. But, and again, I'll round up, so about $4.87. And there's my answer. So how do you know when you don't have a solution or when there are infinite solutions? So you will have no solution if at any point while you're doing your combinations, you get a false equation, just like with two variables. Oops, a false equation, not equations. So that could be, as an example, 0 equals 5, or anything that is just not true. That is a false statement, right? It could be 1 equals 2. Okay, none of that is going to be true. So that tells you that there is no solution. There is nowhere in the three-dimensional world where these three planes intersect. Okay? The other possible answer is that you get infinite solutions. Okay, if at any point, hopefully you already know what this is going to look like, you get an identity, then you know that it is a infinite solutions problem, or that is your solution. So basically, for example, maybe it's 5 equals 5, right? Any true statement like that where it's something equaling itself, that's going to tell you that you have infinitely many solutions. And if it's infinitely many solutions, that means that basically the 3 planes that are represented by the 3 equations are meeting or intersecting in a line. And as you know, a line goes on and on and on forever in both directions, so every single point on that line is going to be a solution. And I'm not going to draw this picture. I encourage you to look at page 177. There are beautiful pictures there of planes intersecting in a point, planes intersecting in a line, and planes not intersecting at all. So again, one solution means that they are, so if you actually find an ordered triple like we did here, and for the most part, if it's not a word problem, you're going to want to write that ordered triple as 3 points, okay? So jelly beans was my first point. Chocolates came next in my equations. And then last one. Or if this was on a coordinate system, then this would be X, Y, Z. So you want to put them in whatever order, maybe alphabetical order. In our word problem here, we really wanted to just answer this question, okay? But in our problem here, that meant that I had 3 planes intersecting in a point. Our problem here, no solution. If you have no solution, that means that the 3 planes never ever touch. And if you have infinite solutions, again, you have 3 planes that are intersecting in a line. And again, look at page 177.